Welcome back. So we have seen what is possible with machine learning in the last 2 years, 5 years, 10 years, dramatic advances in machine learning. And we understand now kind of the process of, what machine learning is, essentially building models from data with optimization. Today, I want to talk about some of these kind of advanced tie-ins to physics and engineering and scientific systems. Specifically, how do we do physics-informed machine learning and build physical models from data via optimization? Very, very important when we want to have our systems be more generalizable beyond their training data, more interpretable to a human, more likely to be certifiable and safe for use in safety-critical systems like self-driving cars and autopilots and designing, jet engines and aircraft wings, things like that. This is a passion of mine. There's going to be, a whole series, probably a whole kind of like short course or boot camp on physics-informed machine learning, maybe several, but this is just the very high-level overview. So oftentimes you can get a lot of benefit just by building models from data with optimization. Just from data, you can build models of physical systems, but usually it's the case that when you bake in some prior physical knowledge into these machine learning algorithms, you usually get much better performance and robustness with much less training data and simpler models. Okay, so a lot of benefits here. So we'll just recap kind of the 5 key pieces of building a machine learning model. And these are all human endeavors, right? So machine learning is not just a turnkey automated process. This is a human tool for humans to build models. So you have to choose what you're modeling. You have to decide what data you're going to use or you have available to train that model. You pick an architecture like a neural network, a specific neural network that you think is going to do a good job of modeling that input-output function that you're trying to model. You choose a loss function, you write down an optimization problem, something that a function you're going to try to minimize or maximize that tells you if you did a good job. And then you employ some optimization algorithm to essentially train the parameters, the free parameters of this architecture to minimize this loss function averaged over the training data. That's what machine learning is. And physics-informed machine learning, essentially there are opportunities to embed physics into every single one of these steps. Okay, and so I could give a whole lecture on how you embed physics into every single one of these pieces. I'm going to have a whole series on this, but at a very high level, I just want to motivate what this might look like. Okay, first off, what do I mean by physics? There's a lot of definitions of physics and the kinds of physics you can bake into these models. Physics could mean mass is conserved, or mass or momentum or energy are conserved. Lots of systems, if I'm trying to use machine learning to improve a computational fluid dynamics solver, I know that my fluid has mass and momentum and energy conservation. And so I might want that physics to be preserved or embedded in my machine learning model somehow at some stage in my process. I might know that my system has a symmetry. So conservation laws are deeply related to invariance. So essentially, anytime I have an invariant, it is something that is conserved. And Noether's theorem from classical physics, one of the best, my favorite theorems in all of mathematical physics, Noether's theorem says that every fundamental symmetry gives rise to an invariant or a conserved quantity. And so symmetries are another way that we embed or represent physics that we want to enforce in these models, okay? And you can think that almost every class of physics is essentially defined by its symmetries and how the system responds and acts and transforms under different symmetries. Classical mechanics has its own set of symmetries, typically things like rotations and translations. My physics should be invariant to rotations and translations. Quantum mechanics has a different set of symmetries. General relativity has its own set of symmetries. Physics is essentially defined by the symmetries that are preserved in that system. And so symmetries is another notion of physics that I want to be able to embed in my models. Another good example, and this is a little bit more nebulous, is the notion of simplicity or parsimony. Most of our physical laws, if they don't overfit, if they generalize, tend to be quite simple. Newton's second law, F equals ma, Einstein's E equals mc squared. These are very simple expressions. In fact, they are the simplest expressions required to describe our observations, and you can't make them simpler very easily. And so that notion of parsimony or simplicity tends to allow our models to generalize and to be more interpretable and understandable. That's philosophical, it begs the question why, but it happens to be true. And so I might want parsimony or simplicity to be a design feature in some of these stages of machine learning. So I'll just give you a couple of examples. Deciding on an objective is probably the easiest way to embed physics. I'm just going to decide to model a physical system. If I'm modeling the trajectories of cannonballs, I'm already modeling a physical system. So that's physics modeling in its simplest case. Oftentimes, I try to model differential equations, x dot equals f of x. And that inherently has some kind of physicality because you're dealing with time series data that has rules according to a dynamical system. Data. How do I embed physics into the data? This is what I loosely think of as kind of the Google approach to embedding physics in your system, which is if I know that I want my model to have an invariance to rotations and translations, let's say I'm doing an image classifier and I know that the cat that I'm trying to classify is still a cat if it's rotated or translated in the image. The kind of big data approach would be to augment your data with many, many, many examples of that rotated, translated training data. So you can take your data, maybe it's a little bit meager, and you can augment it with rotated, translated versions of that data if you know that your model should be invariant to that. I'd say that's fairly expensive and fairly brute force, but it does kind of work. And if your training data is large enough, like you have all of Google Images or all of Facebook, data, then your data might already have those symmetries kind of built in or baked into the data set. Okay? Oftentimes, we don't have the luxury of that, data augmentation or nearly infinite data. We have to get away with less data. So that's why I actually like to enforce physics in these last three steps. Designing an architecture is a really good way. So, for example, the autoencoder architecture that has this information bottleneck where you choke down to a small dimension, that has a lot of nice regularizing properties of promoting simple models that have less degrees of freedom and less variables, which is kind of a physical concept. There are architectures like you can take something like this autoencoder, and you can constrain that the middle layer, that f function there, maybe it has the structure of the Euler-Lagrange equations or Hamilton's equations. Maybe by construction, I can enforce that my system looks Hamiltonian in that latent variable z, thereby forcing it to be energy conservative. Okay, so by construction, I can often choose an architecture that has kind of physical properties baked into it. If I think about a convolutional neural network, it has translational invariances baked into it. So by construction, I'm going to get translationally invariant models. And there's a whole class of machine learning where you essentially have input layers and output layers that are designed specifically to be invariant under certain symmetry transformations called equivariant neural networks. Very, very powerful class of architectures that by construction satisfies certain symmetry properties. So crafting the loss function is another great place to bake in physics. Let's say, again, I'm a fluids person, so I think about estimating a flow field. I want my flow fields to be divergence free if it's an incompressible fluid. So what I can do is I can add a term in my loss function that has the divergence of my estimated flow field. And again, if that's non-zero, that's a penalty. And so I'm trying, that forces my optimization to try to minimize the divergence of my flow field as a term in the loss function. And you don't have to just do divergence. Anytime you know your partial differential equation, you can essentially add a loss term that says that PDE should be satisfied by the solution. That's the basis of the physics-informed neural network, or PIN architecture. Very, very popular, very, very useful architecture. Now, adding a penalty term in the loss function is a great idea, but it only gives the suggestion of being physical because it's still competing that loss term with all of the other loss terms, like getting a good, model error and model fit. And so you will definitely get this compromise solution where it is more physical, but it's not, perfect divergence free like you would get from a classical numerical solver. And then finally, oftentimes you can actually design optimization algorithms directly so that if you know that there is a subclass of parameters in your architecture that are physical, that adhere to certain symmetries, you can often do constrained optimization to force yourself to enforce those symmetries or those conservation properties. So I personally, in my line of work and lab, like to mostly focus on 3 and 5, but they do require like a bit more effort. Designing an optimization algorithm is sometimes challenging. Choosing an architecture to be structure preserving, it definitely requires some knowledge of the structure that you're trying to preserve. The fourth one is a really good kind of middle ground where it's easy to implement and it does promote physicality, maybe not in as hard of a constrained, rigid way as 3 and 5. Lots of options, big field, changing and evolving every day. And so, it's an exciting field, but it's also in its infancy right now. So you can definitely improve machine learning models by, adding physics loss functions and things like that, and constraints and symmetries. But our ability to actually learn what we would call physics from data is still in its infancy. And this is a lot of what my lab works on and our colleagues and collaborators' labs across the country and across the world. But the state of the art is still, we're still really taking baby steps right now. So this is a video of a pendulum oscillating, pretty simple mechanical system. We could write down the differential equation for this. It's very, very simple nonlinear oscillator. For small amplitudes, it's a linear oscillator. And so what we might want to do with a physics-informed machine learning algorithm is try to learn from this megapixel image, from these million measurements every instant in time. We might want to compress this down to a low-dimensional latent space and learn that there are only a few degrees of freedom that actually characterize the system. In this case, there should be 2 variables that matter, theta and theta dot. That from theta and theta dot, I can perfectly reconstruct this field. So I should be able to compress this down to 2 numbers and then use those 2 numbers to reconstruct the full image. And from those 2 numbers, I don't just want a compression, and I don't just want a predictive model that's a huge deep neural network that a human can't understand. What I would really like is for there to be some simple, parsimonious, human interpretable differential equation, a physics model in the middle that actually describes how those variables evolve in time. Now, this we can actually do. We can take videos and learn the latent variables and actually learn with machine learning the differential equations that govern that behavior, but currently only for relatively simple systems. This is kind of, I might be exaggerating a little bit, but this is, near the frontier of what we can do. So we're trying to push the boundaries of this to learn really hard physics that we don't know the answer to. So, we want to take images from active matter, non-Newtonian fluids, disease dynamics, flocking behavior, brain data, and we want to be able to do the same thing, learn the latent representations and the differential equations that describe the data that a human could then understand and read, and that would have some chance of generalizing. Let's say I increase the angle of this thing. A classical neural network's probably going to fail, but if I learn the physics, I'll be able to handle that new initial condition that wasn't in my training data. So that's kind of what I'm talking about with physics-informed machine learning. Again, still the frontiers of our knowledge, still an active area of research. Just to recap, stage 1 is set up the problem. Stage 2 is find the training data. Stage 3 is pick an architecture that can represent the input-output function, and it can be parameterized by some free parameters theta that you're going to tweak. Step 4 is design some loss function that you're going to try to minimize to tell you if you did a good job. And step 5 is optimize over those parameters, tune those free parameters to minimize that loss function across the training data. Okay, that's the kind of the stages of machine learning, and you have an opportunity to embed physics in every single stage of this process. Okay, we're going to have a lot more. We're going to dig into each of those subcategories, lots of physical examples. We're going to talk about what works and what doesn't work, but that's, a longer story. So this is just the intro overview. All right, thank you.